All right, and let me take you to the practice quiz. So 20 mile per hour winds moving the direction 23 degrees north of east. Write this vector u in the form u1, u2. Okay, we're getting some noise, so check to see that you're muted. Thirty seconds more. Okay, so if I have east over here and north here, 23 degrees north of east would mean go east and turn 23 degrees towards the north. So this is 23 degrees. And then you've got this, and let me blow that triangle up a bit. This is 23 degrees. And we just have this standard right triangle. And this, the adjacent part is 23 degrees, 23 cosine. Hold it. 20, not 23. Cosine of 23 degrees, because the cosine extracts the horizontal component, and this is 20 sine 23 degrees. And so then those are the two components, the u1 is this, the u2 is this. If you're not comfortable with the cosine extracting the horizontal, you could have done SOHCAHTOA. The cosine is the adjacent over the hypotenuse. So this we know is 20. And then this, we don't know what it is, we'll call it x. You could just say cosine of 23 degrees is the adjacent x over 20. And then you cross multiply x equal to 20 cosine 23 degrees. And that would give you the horizontal component, etc. Similarly, do it with the sine to get the other one. All right, a little bit of feedback on number 1, please. Okay. The locomotion of a boat in still water would be represented by vector A. So here's a river, boundaries of the river in blue. Because of the current, its actual locomotion is B. Represent the current as a vector and label it in terms of A and B. Okay, 30 seconds more. Alright, so if the boat was really going to go this way in still water, must have been that the current added this to the movement. So boat plus the current gave you the actual direction right here. And what is this? Well, this is not A plus B, but remember when we put the tails together from one to the other, that's the difference. It's either A minus B or B minus A. Is it A minus B? We're going from A to B. This is the starting point, the tip of that. This is where we finish our destination. And no, this is not how we do it. It's always the change is destination minus starting point. So it's B minus A. That is what this is right here. Alright, give me a little feedback on number 2. Okay, I often do something else first, slowly get to it. Yep, same way I often work. This could, yes, we could say that it's about displacement, destination. In a way, this is, yes, kind of like the change. How did A change to B? What did I have to add to A to get to B is also that difference. I had to add the current to the A to get to B. And let's go to number 3. State the two-space distance formula, an ordinary distance formula that you're used to. Two space because it's two-dimensional space, x-axis and y-axis. Thirty seconds more. Okay, so you can just state the distance formula D equals from memory. If you're like me though, you have a hard time remembering such formulas. And I might need to construct something like this. Suppose this point was x1, y1 for my first point. This is the point x2, y2. Then to find this distance D between them, I would construct this. So this is x1 units over. over here, this is x2 units over. So this must be x2 minus x1. This point, this height is y1. This height is y2. So this change in the height is destination minus start, the difference. And Pythagorean theorem says this squared is equal to this squared plus this squared. And then you square root both sides, and it gives you d equals the square root x2 minus x1 squared plus y2 minus y1 squared. There's the distance formula. And give me a little feedback on number 3. Yep, doesn't look any different. It's derived from the Pythagorean theorem. Yep. Okay. Alright, the reason why I'm reviewing that is today's topic is going to be going to 3 space, vectors in 3-dimensional space. And one of the things we're going to do is extend this formula to the 3 space distance formula. And we want this as a foundation to extend it. Alright, write the definition of a circle, not the equation of a circle, but the definition. Now, this one's kind of unusual. And how in the world would you define a circle in a mathematically precise way? So I'm going to have you go to your groups and take a stab at a definition. Type it up, but don't hit enter yet. And even if it's really crazy, try something. And of course, if you can't think of anything, you can always type in, came up with a blank. But again, you're going to get more out of this course if you can get yourself to just try, even if it seems really crazy. Okay, go ahead and hit enter and look at all the others. You might talk about it briefly. Right, make sure you're rotating group spokesman for the day, group leader. Hopefully that's what you're doing right at the beginning of class. Is reminding who is the group spokesman. And group 2. What do you have here? You can always say pass too.
I said that there was a 2D shape with rounded edges where every point is equidistant from the center.
Okay, and did you have any other suggestions as well?
Then Cameron said it's a circle. A circle is a shape with an infinite number of sides, but with one focus.
Okay.
And that was all we had.
Okay, that's cool. Let me focus on your part with the and my little stylus. Oh, here it is. You said equidistance from the center. And that's what we're gonna, a formal definition, a mathematical definition of a circle would look something like this. The set of all points. Now here would be an important little phrase, in a plane. If you leave out this in a plane, you're going to wind up getting a sphere instead of a circle. The set of all points in a plane, a distance, we could call it R, from the point, we could call it HK. And then what does that define? That defines if here is HK and here is a distance R, that defines, well, we can have R be like a string. You put a pencil, tie it on the end of your string, you get to move it all around, and it maps out a circle. So that's really coinciding with that idea of equal distance from a fixed point over here. All right, and questions. Questions on any of the homework problems or any concepts or anything?
Can we go over 55?
Number 55. Okay, and got it. And this is from 3.1. Is that right? Yeah.
Yeah.
That's right.
Determine necessary airspeed and heading that a pilot must maintain in order to fly her commercial jet north at a speed of 480 miles per hour relative to the ground in a crosswind that is blowing 60 degrees south of east at 20 miles per hour. Alright, so let me have a grid. She wants to be going exactly north, and that at 480. Magnitude being 480. But the crosswind is blowing 60 degrees south of east. So here is east, here is south. So the crosswind is blowing like this. 60 degrees, a little more than half of this. Just like this. This is 60 degrees. Now it's not just blowing here, it's blowing everywhere. And it's 20, magnitude of 20. Alright, so what we need is something that will go up here. And we'll end up, so if I put this one here, it's giving me a hard time. This should be the same length and direction as that one. Just imagine it is if it's not. So that when we do this one, plus this one, we'll get this one right here. Everybody following that so far? My picture makes sense?
Are you putting the 60 degrees up top?
Yes, I moved this one because the way that she's actually got to fly, this is her flight in still air, how she would be moving if she was going in still air. And then when you add to that the wind, 60 degrees south of east, you've got to end up at, so this 60 degrees south of east, I could be drawing it all over. The wind is everywhere. And so I could put it there as well. Kylie, does that make sense?
Yeah, that makes sense.
Okay. So now we have the visual image. How am I going to turn this into some math stuff to figure these things out? How do I actually get
I and J components?
Pardon? I and J? Okay.
I and J components.
Components. So that's the preferred components if we're going to be adding. If you have things like south of east, 60 degrees south of east, and so on, you can't add them like that. You got to get them into that.
Can you do the distance formula then? Or no, the Pythagorean theorem then?
If it was a right triangle, but I don't think this is going to be a right triangle.
Wouldn't we just use like the sine or cosine or tangent?
Yep. And we'll add component by component. Okay, so we'll take this one. Its components are 0, 480. We'll take this green one. Its components are, now it's 20. Cosine of 60, remember the cosine extracts the horizontal component, just like the practice quiz. And then, now what we call that 60 degrees as, erase things here. We call 60 degrees the reference angle. And it's actually going to give us a negative y component. So I'm going to put that negative sign up here. So you don't have to work with negative 60 degrees. You just stick in negatives when you need them. Okay. And then the relationship of these things, this one we don't know what it is. Let's call its x component x and its y component y. But then we have this relationship. This plus this, it's got to give you this. This plus this, it's got to give you this. And then we could figure out the x and the y. Are we following?
Yes.
And Matthew, is that enough? Does that answer your question?
Well, I'd gone through it and and then I checked it in the back of the book. Since it's an odd number, my answer was slightly off what theirs was.
You're close, but not quite.
Yeah, so my answer was like 497 miles per hour, and I think the answer in the book was like 492 or 490 or something like that.
All right, I think, so the answer should turn out to be, since x plus this is equal to 0, it should be negative 20 cosine of 60 degrees. And then the y plus that is equal to that. So the y should be 480 plus 20 sine 60. So that's what we should want to be getting.
That's what I and Matt have.
And that doesn't agree with the back of the book?
I didn't even bother with the back of the book.
It was number 55.
The back of the book has something a little different?
So they say it's 490.3, and so
For the first coordinate? Or for the second coordinate?
they don't give in terms of coordinates. They just say approximately 490.3 miles per hour with a heading of about 1.2 degrees west.
Okay. All right, so that's appropriate. Because the answer was in terms of angles and magnitudes, or the question was stated that way, so the answer should also be stated in the same way that the question was stated.
It's just that their answer is 490.3, but when we put that into decimals, what we got would be 497 miles per hour instead of
Same here.
90.
Correct. Okay.
Same here.
So I got that same answer, and that's why I was just gonna. I don't know if the book's wrong or
All right.
I've got the same answer as you, Matt.
yeah.
My magnitude is 497 point whatever miles per hour and a heading of 91.15 degrees.
So I think if you add those two up, the magnitude is 492.95. Is that close to the book answer?
All right. So this.
Oh, that's interesting.
If you add those two together, that gives you the angle xy, which gives you the whole distance.
You need to use the Pythagorean theorem, though, to find the magnitude.
Right.
So
That's
that
what I'm
works.
using.
Okay, so this turns out to be this.
I thought you said the Pythagorean theorem only applies to right angles.
Okay, that's this one
We-
right here.
We made a right angle.
So then, if you
Oh, I
drop
see.
this straight down, right. So what we have is this part is negative 10 right here. And this part is the vertical height right there. And then the Pythagorean theorem will get us this magnitude of that red part. 497.32. And now if we square each of those and then add them together, take the square root. So it's 100.
It's going to be slightly larger than 497.3, and I have something slightly larger than 497.3. I'm going to say the book's wrong on this one.
Yeah. And then raise to 0.5. Yeah, I get about 497.4. And the book is saying what? 400 and
90.2.
yeah, they're wrong. They're
Book is way out of place.
Yep. So we'll just put a little note here. Textbook is wrong. All right. Any other questions?
I think I do have one.
Yeah.
For problem 50, find the find the velocity v of an ocean freighter that is traveling northeast, 45 degrees east of north at 40 kilometers per hour. It's like, find the velocity. Are they asking us to find the velocity after they give us the velocity?
Okay, so what's the nature of this question? Let me get a little more space here.
I had to look at 51 in the back of the book in order to figure out what they were really after.
Okay. So let me process this myself. Find the velocity v of an ocean freighter that's traveling
To the best of our
to the best, just say 40 kilometers per hour.
yeah. So to the best of my knowledge, velocity is basically a speed and a direction. So they've just given us the speed and a direction. So after looking at 51, after looking at the solution for 51,
What I did is, I don't know if I did it right, but I just like componentified the velocity into like the velocity going east and the velocity to the north.
Is that what they did for 51 in the back of the book, Cameron?
It is what they did.
Yes. Okay. So they just
That's
want you
weird.
to give it, and they give it in this form, where they give you the direction and the magnitude, and they just want it in component form. And that's all they want you to do. Okay. And so that's much like problem 1 in our practice quiz today. All right, anything else? All right, let's go to 13.2, vectors in 3 dimensions. All right, and so we'll be in 3 space this whole semester. That's what Calculus 3 is. And I've had students who have taken this course and Physics 2, the calculus-based Physics 2, same semester, and those students usually get very excited somewhere in the middle of the semester, and they say, "Oh my gosh, we're doing the same stuff," and and in a physics class they just say, "Do this, and you'll get this result." And then this is how you use it. But here we kind of go into detail, and we see why you're supposed to do this, and so on, and so they get a lot of insight, and they get very, very excited. Let's set up our 3-dimensional coordinate system. You have to use, and this is related to breakthroughs in art, in the history of mathematics. Breakthroughs in drawing greatly affected mathematics, and the 3-dimensional perspective is the one here. So we're going to have the y-axis be horizontal, and that's kind of like the x-axis was. We're going to have the z-axis be vertical, kind of like the y-axis was. And then we're going to use perspective. Imagine the x-axis. So these two are, if I was drawing on the blackboard at school, these two are on the blackboard, or they're on your sheet of paper. And now the x-axis, you imagine it coming out of the board straight out at you in the audience. So, but we draw it with perspective here. We put it at an angle. We say this is the x-axis. Now, if we were physically in the classroom, and it's helpful, so you're just going to have to imagine that we're there for a minute. I'd be going, so imagine you're in the class, I'm standing up at the board. And you're looking at me, and then to your left, up at the front of the classroom, down at the floor, we're going to say, all right, that point in the corner of the room here, is the origin. And then here's the chalkboard over here on this wall. And then underneath the chalkboard, along the floor, that's the y-axis, the z-axis straight up. The x-axis comes out into the classroom, and y'all are sitting out here. Okay, everybody visualizing the coordinate system we're going to use. All right. Now, when you're doing this in computer graphics, you might see these x, y, and z differently. You might see this horizontal one as the x, and so on. And so that, and in fact, you can grab these axes in most computer-based systems that will draw in 3 space for you. You grab the axis and then you pull on it, and it rotates everything around for you. And rotating all this is fine, but what's going to be preserved under all the rotations is what we call the right-hand rule. So the right-hand rule is if I take my right hand, now I'm going to switch to the camera here. Now you're seeing me. Okay. The right-hand rule. I've got a sheet of paper. Here's my Wacom tablet. Too bad I have to hold it horizontally. Alright, but here's the idea. I'm going to take my hand and place it along the bottom of my hand, place it along the x-axis. And then I curl it towards the y-axis. So here's the x-axis. The y-axis was over here, so I'm curling it like this. Then my thumb is going to be pointing towards the positive direction of the z-axis. Not down here, but up there. So put your hand on the x-axis and rotate. Now let's go back to our image here. Notice, if you put your hand out, so the bottom of your hand is along this x-axis here, and then you curled it towards the y-axis, then your thumb points up. So, bottom hand, x-axis, curl, hand, toward the y-axis. Thumb points at positive z-axis. Okay. So the right-hand rule is important for us to get oriented. We need this kind of rule so that, like, you know, when they make screws, so that everybody screws and you turn to the right and it screws in instead of screws out when you're using a screwdriver and all this stuff. So this kind of orientation can get everybody with common definitions.
I have a question.
Yes.
I can't use my right hand for that. I have to use my left hand. Is it supposed to be? I'm just wondering if the right hand rule is be with your right hand, or is it just called that?
No, it's if I use my left hand, it won't work for me.
But if you put your left hand flush with the paper and curl your fingers towards the y-axis and your thumb pointing z, that works. But if I try it with my right hand, then my fingers are curled towards the z-axis.
Anybody else seeing it that way?
I learned in physics that for some reason you have to use your right hand. It doesn't work with your left.
That's toward. Now you have to do it towards the positive y-axis too. Curl hand towards the positive y-axis. Let me go back to the camera. Alright. So let's call this, if I call this the x-axis. Oh, boy, it's so hard to do. Alright, call this the x-axis, this the y-axis. Curl, and then this is going to be the positive z-axis up here. And over here, if I'm having my hand, where's my hand painting? My hand over here, but I'd have to whip it around so that the bottom of his hand is on this. Then it's going to curl towards the Y and the thumb would point up at the Z. Kylie, if you're still struggling with this, we can look at it during the break.
The question? Yeah, so I tried the right-handed coordinate system, but at times it seems to confusing to me. So I just plainly think, and y coordinate is usually in the two-dimensional plane is the x-axis, and the z-axis will be y, and x-axis towards you. So just in your imagination. So that if I have that concept in my mind, then they will be okay to understand.
That's right. Yeah, even if you didn't totally get the right hand rule, yeah, it's not going to be a big problem. Yeah, if you can just set this up each time like this. Y and the Z are on the board, and the x-axis, imagine it coming out at you. That'll be okay.
Oh, I think I see it. I was looking at the textbook. So if the x-axis was to go straight through y and z in between, then you put your hand there, right? And then the z goes all the way up.
I'm not sure what you mean by that.
Well, z goes in the three-dimensional, so depth, while x and y are your directions.
Yes, the x and y axis, if we were in the physical classroom, they would make up the floor. And then the z is the height off the floor that you're at. Is that making sense?
Yeah, it makes more sense.
Okay. All right, let's move on to, now there's the coordinate planes. All right, so we have XY coordinate plane. And if we were in the corner of the room, the XY coordinate plane would be the floor. And then the XZ coordinate plane would be the wall. And the YZ coordinate plane would be the wall containing the blackboard. And those planes stretch out forever. but you have 3 coordinate planes in 3 space. And remember in 2 space, we have, instead of 4 quadrants,
we have 8.
Very good. 8. And what are we going to call these things? We call them octants. Now, it's going to divide the world up into, because you imagine the x and y axis comes back over here, and the x axis comes back this way, y axis comes down here. So, if all the coordinates are positive, we're in the classroom. But then we're on the other side of this wall if the y is negative. And then we're maybe outside the building if both x and y are negative. And then on the other side of this wall, so we have 4 octants above ground, and then we have 4 more underground. Okay, so we're also used to the unit basis vectors, and we're used to I, J, and now we have K. I is 1, 0, 0. J is, oops, this is supposed to be a bracket. J is 0, 1, 0, and K is 0, 0, 1. 1 unit in the X, Y, or Z direction. Alright, let's come on down to in 3 space. Functions are no longer of a single variable. In 2 space, our functions look like this. Oops. Y equals f of x. In 3 space, our functions will look like this. Z is equal to a function of x and y. And Z might be, for instance, if we were in a physical classroom, I'd be pointing out how the XY plane is the floor. And then suppose I dumped a whole bunch of dirt into the room, and there were hills and, you know, portions where there's lots of dirt and portions where there's just a little dirt. The height of the dirt at any XY coordinate could be called Z. And then this would create a function that's a surface in 3 space. And if I put a tarp on top of all of this dirt, that is the surface. That tarp, if you think of it as infinitely thin, is the surface that's created by this 3 space function. Alright. So those are some ways to visualize what kind of a function in 3 space might look like. And let me have you take your best stab at drawing the point 2, 3, 1 in 3 space. A single point, draw it in 3 space. I'm going to give you 30 seconds. Okay, I could just put a dot anywhere and say, oh, that's the point 2, 3, 1. But to give it a little perspective, I want to have my y and z axis. It's kind of like the traditional x and y. Imagine the x axis coming out straight with the chalkboard out at you, my x axis. So to give it some perspective, I'd say I go out 2 units in the x direction. Then I go 3 units in the y direction. Now, when I go 2 and 3, I could kind of visualize this. So suppose we were in the physical classroom and I went to the upper left, lower left-hand corner of the room from your perspective as you're looking at me. And we found this point on the floor of the room. And then we go straight up 1 unit from there. And then we make our point. So now, if I didn't put these dotted lines over here, and this is the crazy thing about 3 space, if I didn't put those dotted lines, you wind up getting a dot. Where is that, relatively speaking, about here? And is that dot in the octant below, above, behind? It could be anywhere. You cannot tell if you just place dots like this. And that's why this drawing in perspective, it usually needs the aid of a computer to be able to resolve something like just a dot in there. Because then you'd grab one of these axes and rotate it around, and you'd look at that point from all these different perspectives, and then you'd kind of be able to get a sense of where that dot is. So we kind of need some of this stuff otherwise to be able to sense where we are. We have a much more difficult time drawing shapes in 3 space because of this perspective issue. Now, together we're going to find the distance from the origin to 2, 3, 1. We have a picture of 2, 3, 1. And while we're at it, we'll come up with the 3 space distance formula. So I want to find the distance from 0, 0, 0 to this point. So I want to find the length of that line segment. We'll call that D. Distance from 0, 0, 0 to 2, 3, 1. And I'm going to first find the distance to here, to this, where the 2 blue dotted lines connect. And if I do that, the 2 blue dotted lines, let's make this. Where this is 2, this is 3, And then this dotted line here. These are really at right angles. They're just from perspective, they don't look like right angles. But this 2 is also over here. So this dotted line down here is just, we use the Pythagorean theorem. So this dotted line here is the square root of this squared plus this squared, 9 plus 4, so it's the square root of 13. Okay, and then now we have this other triangle. This other triangle is this dotted line, and then straight up 1. So this one was square root of 13 in length, and this one was 1 in length. And then we're trying to find this distance. And these are at right angles to one another. So once again, we'll use the Pythagorean theorem. And D is going to be the square root of square root of 13 squared plus 1 squared, which is the square root of 13 plus 1, square root of 14. Okay, so we found it. D is the square root of 14. So I'm going to give you a challenge if you want to. You can just take a 15-minute break and just watch me come up with the generalized distance formula in 3 space. But if you feel like you want the challenge, you say, all right, what does square root of 14 have to do with this? And the point 0, 0, 0, and what's the general 3-phase distance formula? And maybe even drawing a picture that demonstrates the general 3-space distance formula, kind of like we had a picture for the 2-space distance formula. Alright, so, and if anybody comes up with that and wants to share that, they can, or if they want to just keep it to themselves, that's fine too. But we'll start again at so at 6:44 p.m. 15-minute break. And I'll start by asking if anybody wants to share what they found out about this. And we'll go from there. Now, before I take my break, does anybody need to talk to me individually? All right. See you in 15 minutes. Okay, so does anybody have anything to share about finding the general three-space distance formula?
This is Rowan. I think it's really similar to the two-dimensional distance formula, but you add another term, which is z, like z2 minus z1 squared.
So
And then like it's all within the square root.
So it's going to be d equals the square root of, how do I start it?
X2 minus x1 squared
Okay.
plus y2 minus y1 squared plus z2 minus z1.
And do you have a picture that might kind of illustrate it?
I mean, like, it's just like you kind of already drew it up there. Like,
Yeah.
we've got a distance formula on the xy plane, and then we kind of do a second distance formula on like a plane that intersects that plane. And then but you don't need to cut it into two steps because you're taking the square root of everything, so you can just include it all in one square root sign.
All right. And what we see if we call this point 0, 0, 0, and call this point x1, y1, z1. Now, you could generalize this even further by calling this one x2, y2, z2, and calling this x1, y1, z1, and then we'll get the full distance formula. But we'll get a simplified version of this by, if we just do this, then this portion right here is going to wind up being, because it's got x1 and y1 as its two components for this rectangle, the square root of x1 squared plus, it's really x1 minus 0 squared plus y1 squared. And then you have this vertical distance over here. So this would wind up getting replaced with square root x1 squared plus y1 squared. This would get replaced with z1. And then when you take the square root of this squared plus this squared, you just get all three of these, x1 squared plus y1 squared plus z1 squared. And so we could reconstruct this three-space distance formula. Alright, so we're going to need that at different times, and it's just natural extension of the two-space distance formula. And let's go to spheres. Alright, now, formal definition of a sphere. It's a set of all points. Now we leave off in a plane a fixed distance, which could be r, from a fixed point, which could be h, k, l. And with this, let's come up with a problem. problem. Write the equation of the sphere whose center is 1, 4, 2, and radius is 3. Now, tools at your disposal. As we figured out a three-space distance formula, we have a general idea of how a sphere is defined. So, what I want you to do is work individually on this, and as you come up with something, maybe it's just how to get going, or maybe it's the whole equation, or just maybe it's a simple idea, input it into your group chat, and then in a little bit I will call on the group. Okay, so start out by typing up whatever conclusions you're coming up with, but don't hit enter quite yet. Let people work on their own for a while first. And any ideas you've got, go ahead and you can go ahead and hit enter, do group chats, and talk this out some more. Okay, group 1, any ideas?
Yeah, Rowan had x minus 1 squared plus y minus 4 squared plus c minus 2 squared equals 3 squared.
I think that's makes sense.
Why does this make sense? Where in the world does this come from?
Well, if you think about the formula for a circle, so you would have well, isn't it the same thing as the distance equation that we did for rectangle? But since we have a radius, it gives you kind of what the diameter would be of the sphere, since you're squaring it.
That's right. That's right. And I liked the way you said that it's similar to the equation of a circle. If I just imagine this hand was bigger and I was covering up all of this, this is a circle in 2 space. And just like the 3 space distance formula just had an extra component, same thing with this sphere, just has this extra term in here. And let's go with a visual on this. Let me draw it like this. So if I have don't cross this. So X, Y, and Z. So I'm going to go 1 in the X direction, 4 in the Y direction, and then I'm going to come up 2 units from there. I'll be right here. That's my center of my circle. That's the point 1, 4, 2. Now the sphere has all points that are 3 units away from this point. I'm going to take just one of those points. And I'm going to call it X, Y, and Z. Now, every point X, Y, Z that is 3 units away from this point will be on the sphere. When I leave it as a general point, X, Y, and Z, and then I do the distance formula. The distance formula is D, we just came up with that, it's up here. But if we square both sides of that equation, that distance formula is the same as D squared equals x2 minus x1 squared plus y2 minus y1 squared, c2 minus z1 squared, or in this case, 3 squared is equal to difference in the x's, difference in the y's, difference in the z's, and I get this, which is exactly the equation that was given over here. This is the equation of a sphere. And not all points x, y, z are going to satisfy this equation. Only the ones that are precisely 3 units away. And then that, if you had a string there, you get to bend this string in every direction now, and it maps out the sphere. Okay. So from here, let's yes.
A quick comment. So it's a sphere. The sphere is actually the three-dimensional version of a circle.
Correct. With a hollow interior.
Right, hollow. So since the ball is the volume, the whole entire field inside.
So how would you change this equation? There's one small change you can make, and then you'll have the ball, not the sphere. You'll have the exterior.
Would you?
Yes?
Would you have to cube it?
Nope. Simpler than that.
Square root it.
No. Good guess.
Just change. Oh,
Pardon?
you can just change the equal sign to a greater than or less than. I guess in this case it would be
correct.
3.
You made this less than or equal to 3 squared. Everything else exactly the same. So we're thinking the radius over here could be 3, or it could be 2, or it could be 1, or anything like this, and then all the points inside the sphere will meet this right here. So this is the ball. And if you leave off the equal sign, then it's just the interior of the sphere. Change it to a greater than sign, it's just everything outside of the sphere. So, great point, Susun. Nice to bring that up and connect that into this. All right, so then let's go. We've talked about spheres. So you're ready for this problem now. Problem. Make this one bigger. Write the standard form of the equation of a sphere with radius r and center h, k, l. And I'll give you a minute. And when you come up with an answer, type it into your group chat, but don't type it in yet. I mean, you can type it in now, but don't hit enter yet. Okay, go ahead and hit enter. Talk about it briefly. So group 2, what is the standard form of the equation of sphere?
It's x minus h squared plus y minus k squared plus z minus l squared equals r squared.
Or less than or equal to.
If it was less than or equal to, it would be the ball. Okay, and the alternate form of this is r on this side and the square root of all this stuff on this side. But this is the more typical form that we find this in. And it's exactly the same thing that we were doing over here before. And the picture would only get modified by changing 142 to HKL and then putting those in right up here. And changing this 3 to an R. And let's go to this next one now. Here's three-space equation. How do I know this is three-space? Because it's got x's, y's, and z's in it. And I need to find out what shape this is and to draw it. Anybody have any ideas how I should get started with this?
Can you balance the equation?
How so?
Can you put all the second degrees on one side and first degrees on the other?
That's one way to kind of balance it out. And then what about the constant? 7. Which side should that go on?
Should go in the first degrees.
With the first degrees? Okay. So that's one suggestion for rearranging things. And that's a very important idea. We might want to be rearranging this. Any other ideas about how to rearrange?
Oh, I'm so sorry. I think that you gather with the similar term x squared and x, y squared and y, and z squared and z, and the constant goes to the right side of the equation. And the left side of the equation, you just make a complete square, or like a x plus 2 square, and then you make a complete square. And
move
all
the
the
7
constant,
over to the right, like this.
all the constant to the
Okay.
right.
Very good. And what we're going to wind up doing is
This is an
putting in just the right number here. But
Yeah.
to add the number here, you have to add it over here. And then we'll figure out what to put here, and we have to add it on both sides. And we'll figure out what we have to put here, and we'll add it on both sides. But every single one of these is going to be what we call perfect trinomial square. And we're going to complete the square. Why do we want to complete the square? Because we want to get it into this format. Once we have it something like this, we can identify the center and the radius of the sphere. Everybody following strategy?
yes.
Okay, so completing the square. What's the number that has to go right here? Plus
4.
4. How'd you get 4?
Square root of 2.
Okay.
It's so I think I'm looking at x plus 2 squared.
Okay. So completing the square, you take half of this one, and then you square it to get this. So this is going to be 4. I added 4 to that side, so I add 4 to this side. Now let's go to this one next. What's going to go here?
2.25
You take half of this
and square it.
and square it.
Is it 9/4? The
That's right.
second one.
We'll call it 9/4 on this side. Okay, and then this last one is
And plus
half of
plus
that,
1.
which is 1. 1 squared is 1. And we have to add that to both sides. Now, let's review real quick. Why was it half of that squared? Well, if you take x plus a squared, that's x plus a times x plus a, and you FOIL it out, x squared plus xa plus another xa, you get 2ax plus a squared. And look at, on a perfect trinomial square, that's what this is. What's the relationship between the coefficient here and this thing here? If you take half of this and square it, you always get this. Take half and square. And that's what we were doing each time. Half of this is 2, squared is 4. Half of this, 3/2, squared. Half of this, 1, squared. Alright, so then, each one of these is now a perfect trinomial square. It's set up that way. X plus the square root of that, squared. Y plus 3/2 squared. And you can kind of check it out. If you FOILed this out, you're going to get that. FOIL this out. you're going to get 3 halves y and another 3 halves y, which will add to 3y. Z plus 1 squared. And then we add these together. 11, 12, and then 2 1/4, 14 1/4. And then, so my center, this is a sphere with center at, well, the formula, it has to have minus signs in it. So this is, you really think of this as x minus a -2. So, or in other words, you can take the opposite sign of these. So the center is -2, -3 halves, -1, and the radius is the square root of 14.25. Any questions? Alright. So let's move on. Let's look at linear equations in 3 space. Linear in any space, what makes it linear in 2 space is when the x and the y are to the first power. And same definition, if all the variables are to the first power, x, y, and z are to the first power, we call it a linear equation. And if this was to be graphed, would we get a line? And before we get started with this, let's take a quick vote. Let's go to the main text channel in Discord here and say yes for it's a line, or no, I don't think it's going to be a line. And don't think about it too hard, just your intuition. What does your gut instinct at this point right now tell you? If I graph this in 3 space, would I get a line or not? Alright, so we're getting more votes for a line than for anything else. And I would think, well, why in the hell did they call it a linear equation if it's not a line? So I'd probably be tending to lean towards that as well. Alright, so let's figure out if this is a line or not when we graph it in 3 space. Alright, we'll start with simpler problems. So, if you were to graph x equals 3, x equals 3 really means the same as there's a hidden 1, and there's a hidden 0, and there's a hidden 0. And if you were to make a table of values for this, all x, y, and z values that cause this to be a true statement. Well, can I pick x equals 2?
No.
Absolutely not. There's no way I can adjust y and z to make this true. What does x have to be? 3. What about y? Can I pick y to be 1?
No. Well, I mean, you could.
Yes,
it's
because
multiplying
x
by
is still
0.
3.
Yeah, because it'll get zeroed out. And if you want z to be 4, that's fine.
You get a plane.
And x has to be 3 every time. The y can be whatever it wants. And the z can be whatever it wants. And these just get zeroed out anyway. We are going to get, Cameron is right on target. We're going to wind up getting a plane. The x has to be 3. The y can be any number. And the z can be any number. And so when I graph this is technically a linear equation. But linear equations in 3 space are not going to translate into being a line.
But the equation you showed us only has z, when one z. And isn't it similar to this equation you gave us with the definite answer, which is a constant?
Yes, we're going to have to look at it. And so we're going to build up slowly. We're starting with x equals 3, and then the next one we're going to have 2 variables in it, and then go up to 3 variables. Okay? And then we'll address your issue then. Good questions. All right, so let's continue graphing this. So this is saying that x had to be 3. The y could be anything, the z could be anything. But the x always had to be 3. So what we get is this plane. Right here. Anything on this plane, I can go any direction in the y, any number in the z, and I'll always be on this plane. So although it was a linear equation, it didn't come out to be a line. And then let's go to the next one. X plus y equals 4. This is the same as 1x plus 1y plus 0z is equal to 4. And now, if I made a table of values like I did before, what was the lesson that we got from the table of values? Basically, it's just that z can be anything. So, if I was to graph this in 3 space, I would graph this equation right here. This is a little bit tricky to graph in this because your axes aren't quite the right place. You know, this is going this way and this is going this way. So often, instead of trying to use y equals mx plus b to graph this stuff, I'll just grab a couple quick points. If x is 0, y is 4. If y is 0, x is going to be 4. And I'll pick 0 and 0 often like this. So all I need is 2 points to graph this line. And 1, 2, 3, 4.
So we have an angled plane.
That's right. 3, 4. There's a point. I'm going to draw my line. And then from here, the z could be any height. So I could go from this point, I can go straight up. Any height I want. So I can take any random point and go straight up and make this plane here. So again, this is a linear equation in 3 space, but we don't get a line, we get a plane. The general rule of thumb is linear equations in any space are 1 dimension less than the space you're in. So in 2 space, That's why we go one dimension less, we get a linear equation as a line. In 3 space, linear equation, one dimension less, it's a plane. There are things in 4 space, we can't visualize 4 space. But we know that a linear equation, when there's 4 variables, a linear equation then is then a 3 space object within 4 space. Okay, so when we go to extending this equation out to 3 variables, making it super simple like this. If I had x plus y plus z is equal to 4, I would start with, alright, let's suppose z is 0. Then I'm going to be in the xy plane. Because remember, z is the height that we're at, so we're on the floor now, in the xy plane, and in the xy plane, I'm just going to get x plus y equals 4, which is the same line that we had before. X plus y equals 4 was that green line. Now, when z is equal to 1, we're not going to be in the xy plane anymore. We're going to be 1 foot above the floor. And we're going to wind up getting x plus y plus 1 equals 4, which will reduce to x plus y, subtract 1 from both sides, equals 3. So what does this do? That shifts this line. X plus y equals 3. If I was to graph that, that would be going to this x-intercept and this y-intercept, and it would shift the line in this bit of a direction, kind of back towards the origin a little bit. But it's up 1 unit in height as well. We could keep doing this, and we could wind up seeing that we're going to get a plane, but this plane isn't a vertical plane anymore. It's tilted. The quick way to draw this graph for this plane is to get 3 points. When you know it's a plane, you just get 3 points and you connect them. And the 3 points I'm going to get are the easiest 3 points. Y, Z, X. I just say, suppose the other 2 are 0. Then this one's got to be a 4. Suppose the other 2 are 0. This one's got to be a 4. The other 2 are 0. This one's got to be a 4. You just find all the intercepts. Find all the intercepts, and then to draw the plane, we imagine this plane is just extended out infinitely in all directions. There we go. Really quick and easy to draw planes in 3 space. You just come up with the line, the intercepts, and connect them all together. Okay. And let's go to number 8.
Did you say that the plane was extended to all directions or just restricted to the triangle?
Yeah, it's not just inside this triangle, but I could have made this triangle a whole lot bigger, you know, and so on, and then that triangle goes out forever like this. So you imagine
it's just the points where the plane intersects with the x and y and z.
It was just easy to draw like this, but we just, you know, imagine this going out further. This sheet of glass is infinitely big.
All right, thank you.
You're welcome.
Unless we restrict ourselves to positive numbers, in which case it stays.
Right. Yeah, if we were just in positive numbers, it would just be this part that we just drew. Good point. All right. So let's look at this problem here. What are the projections of the point 2, 3, 5 on these three planes? The XY, YZ, and XZ planes. The three basic planes. And let me give you a minute to think about this on your own. So we're going to do the second part after we do this first one. And this is good kind of visualization task. You might need to draw this, but whatever you need to do, figure this out. When you get an answer, put it into your group chat, but don't hit enter yet. So give everybody some individual time. Okay, go ahead and hit enter into your group chat. Talk about it for a little bit. Okay, group 1. What in the world does this stuff mean?
Rowan put 2, 3, 3, 5.
So he put,
And
so
2,
on
5.
the XY plane, he said it's 2, 3.
Yeah. Then on the YZ it's 3, 5. And then the XZ is 2, 5. Hisu has put zeros in place of where one of the variables is missing.
Okay. So we could refer to these points kind of with just two coordinates. If you imagine those are the only, that plane is the only plane that exists anymore. So if we did this with 3 coordinates, these points would be, instead of 2, 3, it would be, what, 2, 3, 0?
Yes.
And then instead of 3, 5, it would be
0, 3, 5.
0, 3, 5. And instead of 2, 5, it would be
2, 0, 5.
0, 5. All right. Now, let's look at the XZ. What are the projections of this point onto the XY plane? To the XY plane? Well, to project this onto the XY plane, it makes sense to think, well, you just stick it straight down. And it would be on the floor, and all you had to do was zero out the Z coordinate. Yep. And to go into the YZ plane, so this would be, if we were in a physical classroom, the chalkboard would be up on this plane. Okay, and the projection of this point onto there would be, send it back over to the wall. And so then the X coordinate is 0, and you're just having Y and a Z. So, yep. So, if you just zero out one of the components of a point, that projects it onto one of the planes. And when you zero out the Z, it projects it onto the other two, the XY plane. You zero out the X, it projects it onto the YZ plane, and so on. So these planes are kind of like you're on the XY plane when the Z is 0. You're on the YZ plane when the X is 0, so on. Any questions? Okay, let's go to the second part of this. Draw a rectangular box with the origin and 2, 3, 5 as opposite vertices, and with faces parallel to the coordinate planes. Label all vertices of the box and find the diagonal length of the diagonal of the box. So, let me give you a little bit of time to do this on your own. So this is just an exercise to start getting you comfortable in 3 space. And this box I might extend like this, parallel to this one, parallel to this dotted line, over here, and then I have up here, and then I have parallel to this. Okay, so there I've got my box, and then all these different coordinates. When we're on the XY plane, the Z coordinate is 0. When I'm over here, the X is still, well, now the X is 0. I didn't go out at all. I only went
3,
to the Y.
0.
Yeah. And then the Z is also 0. And this is this point up here. So let's go to this point up here. That's on the YZ plane, so the X is 0. y and z are present. Went over 3, up 5. This point over here only has a z coordinate. The x and the y are both 0. This point over here had an x coordinate, 2. You didn't move any on the y. You moved 5 up on the z. And there's just one more to go. This is on the x-axis, 2 out on the x-axis, but we didn't go off of the x-axis. We didn't go that to the right, and we didn't go up. And then the last thing it asks us to do is find the length of that diagonal, and that's just the distance formula. D squared is equal to these things squared, so d is equal to the square root of 2 minus 0 squared. That's 3 minus 0 squared. That's 5 minus 0 squared. And d is equal to the square root of 4 plus 9 plus 25.
Which is the square root of 38.
38. Thank you.
Good.
All right. Any questions? All right. The homework is 13.2, and I forgot to mention this last time. Groups. I want you to get together outside of class and check one specific problem. Let's look at the homework. Modules. 13.2, vectors in 3 space, vectors in 3 dimensions. And the problem I want you to check together as number 51. All right, we'll stop here for tonight. And y'all have a great weekend. I'll see you on Monday.
Thank you, you too.
Thank you.
Thank you.
Thank you.
Good night.